Yes, we're back at the physics video lecture. It is Fluid Mechanics Video Lecture 10. So last time we were finishing up potential flows, and we did that by discussing sound waves, and in fact we did something unusual there, derived the Eikenall equation for the short wavelength limit. So this is a good thing to have seen, because when you take an optics class, you hear about the short wavelength limit, diffraction, interference, short wavelength, etc. And the formalism for it is never actually described. So we have that Eikenall equation. I'll go ahead and write that down again one more time. So we have A e to the I C of R and T in place of K dot R minus omega T, right? And we get an equation for this, for changing speeds of sound, and that equation is gradient of C squared equals, I'm going to write omega squared over C squared for the case where C is constant, or not C is constant, for the case where omega is constant. And I'll just do one more drawing here with our wave fronts that gradually bend like this, and the idea is the gradient of C is always perpendicular to a wave front, just the way K was for a plane wave front. Good. So this was, I'll write here, recall, this was for the fact that V is gradient phi, and of course, therefore, curl of V is equal to 0. So this was the end of the ideal fluids discussion. So next we're going to go to real fluids, that is to say fluids in which energy dissipation occurs. So next here, I'll just call them real fluid flows. And here we mean there is energy dissipation. There is energy dissipation. That is to say, there is internal friction in the fluid. And that will be characterized by what's called the viscosity. So we'll have a viscosity coefficient. And viscosity. Good. We'll see how we set things up. And what we'll do is we'll set up the equations of motion and describe them, discuss them, and then do channel flows and pipe flows, which is a good application. Get some more pens here. Should do the trick. So we're talking about fluids with viscosity. That's our next topic. And we've reached a point where I can't derive everything for us simply because of time constraints, but I'll motivate everything that we're doing. So the fluids with viscosity, we already mentioned energy dissipation. We're still going to have our conservation of mass. So as we set up our equations, we're starting with what we already have. This doesn't change, the continuity equation. So we've been there, rho B equals 0. But the next point, I'm just going to write Newton's law. And remember, when we transformed Newton's law to the fluid field situation, we had the acceleration dv dt v dot gradient of v. So this was the acceleration side, equaled minus 1 over rho gradient of the pressure. That was the force side. Multiply it over, you'd have had mass times acceleration per unit volume. Okay. Now, what we're going to do is add friction. So we're going to add friction terms to this equation. And the form of the friction terms is motivated by the following. So let's write the form of friction. First of all, there's going to be no friction if you just had a uniform flow. So let's just call this friction F. So F, and for what it's worth, these are all big vectors, okay? So F equals 0 for just V equals constant. If you just had a uniform flow, then that would have to be equal to 0. So the friction's actually going to be dependent on velocity gradients, on relative motion, on layers of fluid trying to slide over each other. So F depends on velocity gradients. And here's one that we've dealt with before, the rotating bucket. So if the velocity field is a uniform rotating bucket type of flow, then there will be no friction either. So, and F is equal to 0, comma, when V is equal to omega cross R. I'll just write here our rotating bucket that we started the thing off with. So those are what's required to, let's say, determine the form of the friction terms. And what we obtain is the following. I'll go ahead and write out the new equation. And we'll write it out and label everything. I think this will be pretty legit. So we obtain, in place of Euler's equation, I'll pull the density out front. Density dV dt plus V dot gradient of V. It's going to be minus the gradient of P, and here come the friction terms, plus eta, that's a viscosity, del squared V, plus, and then this other one is a technical detail. So there's a second viscosity, zeta over 3. Yeah, zeta plus eta over 3. Zeta plus eta over 3. So this is a second viscosity. This is the same one that appears here. Gradient of the divergence of V. So this is referred to as the Navier-Stokes equation. And we're going to simplify it, but let's look at it first. Navier-Stokes equation. This is the general version where there can be some compressibility. We haven't yet said divergence of V is equal to 0. So there will be some frictional term and energy dissipation due to the compressibility, and this one is due to the relative motion. Okay, and of course they're all, you can say, gradients of the velocity, because if the velocity is constant, the whole thing vanishes. Okay, so that's the first thing to be said. The assumption already is that these viscosity coefficients, which are really some kind of thermodynamic quantity, are constant throughout the fluid. So we're assuming that. I can write down some tables of values later on. This one is very rarely dealt with, okay? And above all, what I wanted to note is, and I'll make this leave some room in your notes, this won't take up that much space, but what you want to do is prove that these do vanish for this kind of V right here. So let me just write this as an interesting homework problem. It was one of those stipulations. It's clear that they vanish when V is constant. It's clear that they, clear that they vanish when V is constant, and we're going to prove this here. So let me just write this as homework. Leave some room in your notes. Show that these vanish for V equal omega cross R of the form that we did earlier this semester. So I, J, K at 0, 0, omega, x, y, z. That basic omega where we're rotating about the z-axis. Okay, so that's the one that gives us a two-dimensional flow. So show that all of these vanish, and by the way, we've already shown that the divergence of this velocity field vanishes. Okay. By the way, this is the simple one. This is not the one that diminishes with the nth power or anything like that. This is the basic omega cross R. This is the rotating bucket. We already showed that this vanishes, and then you'll just show that these terms vanish. Won't be hard at all because there's not that much going on. But that'll be, that'll help the motivation of these terms here. This is actually the most general form of these type of internal friction terms that satisfy these stipulations here. Okay, so that's the Navier-Stokes equation. We're going to now restrict ourselves to the case where the divergence of V vanishes, the incompressible flow. So for incompressible flows, incompressible fluids, I'll write flows though. That's something we haven't gotten into. What counts as incompressible? The short answer is if the speed of your fluid flow is much less than the speed of sound in the fluid, and we've talked about sound now, then you can treat it as incompressible. Okay, so I'll write that here without proof. Without proof, incompressible when V is much less than C. Okay, that's part of my notes, but we'll just state it like that. So now we'll take what's left here, d V dt. We'll go ahead and keep the row out front, plus V dot grad V equal to minus 1 over rho minus sine gradient of P plus eta, the row's out front, take this on mine, equals minus gradient of P plus eta del squared of V. So that's del squared applied to each component of V. This form of the Navier-Stokes equation, if you're doing numerical work with fluid mechanics, this is the one that you're going to be dealing with. And the very, very important point that I haven't yet mentioned is the boundary conditions. And they hold true for both of these versions here. That's the source of a lot of the physics. The boundary condition is that the velocity vanishes at a fixed boundary, okay, at a fixed surface, as opposed to just the normal component. So boundary condition, utterly crucial here. Boundary condition, V equals 0 at a fixed surface. So yeah, Very crucial. That's what makes this thing. And yeah, there are plenty of general things to say that I don't want to leave unsaid. For example, we had D'Alembert's paradox some time ago. Let me go ahead and erase this. Where the fluid flowing around the cylinder didn't even exert any force on the cylinder. Okay? Well, that's due to the fact that we have ideal flows with these boundary conditions at the surface, and with these dissipation coefficients, they also exert frictional forces on and with the surface, and so that of course is crucial. That the fluids actually exert a force on the fixed surface. We're not going to have those expressions in here. Okay, they exist. There's a lot of stuff that we can't do, but so yeah, we have that. Like I said, if you are, or I was going to say, if you're doing numerical work, it's going to be with this equation here, okay? And its actual physical boundary conditions. So, energy dissipation we're not going to talk about. What we'll do next is a couple of solutions of this equation here, the Navier-Stokes equation, incompressible flow, for channel flows and for pipe flows. So flow through a channel this is a really important example that'll make a number of things clear. So the flow through a channel, what we're going to do is set up like this. X, Y, Z, and let's see how we're going to bound this thing. At, okay, what am I using here? Yeah, good. So at y equals 0, and at y equals h, we have fixed planes, infinite planes. So this is flow through a channel, infinite. So it's going to be infinite in x and z, and it's going to be between y equals 0 and y equals h. So you just got to visualize that. We have two planes, one at y equals 0, one at y equals h, and there's a flow in the positive x direction. So v, I'll draw it right here. There's 0, there's h, v equals vx alone. So by the symmetry properties that we've set up, there's no vy and there's no vz because it's an infinite channel. So v is equal to vx, and we can also say that it's vx as a function of y. All I mentioned is boundary conditions right now. Vx of 0 is going to vanish, and Vx of y equals h is going to vanish. So so there's our flow with Vx of 0 equals Vx of h equals 0. Okay, very important. And now we can set up this differential equation here. And a lot of things are going to vanish. In fact, the entire left side is going to vanish once we agree that this is reasonable here. First of all, we're looking for a flow that's uniform in time. So dv dt is equal to 0. And then what's left? We only have a Vx, so we can write Vx d over dx plus Vy d over dy z applied to Vx. That's all we have from this term right here. And the d over dx for Vx is 0 because this is just an infinite, infinite channel. So it can't change along there. Then everything else, Vy is vanishing, Vz is vanishing. Okay. So this is also 0. So our entire differential equation, and I should also say something, we're only going to have one gradient in P. We're only going to have dP dx anymore. dP dy and dP dz are going to vanish identically because everything to the left and to the right of them is equal to 0. Okay. So what we end up with now is 0 equals minus dP dx. The rows out on the left, that's fine, good. Plus eta del squared d sub x. Okay. So let's go ahead and write that out. 0 equals minus dP dx plus eta d squared dx squared dy squared plus d squared over dz squared of dx. And see again what we have. The derivatives with respect to x and z are gone, so we just have d squared dy squared. So let's look at what we have here. I'll go ahead and put this on the left side. dP dx is equal to, in fact, I'm going to divide by eta while I'm at it. Over eta dP dx is equal to d squared dy squared dx. Good. So far so good. Now what we have here is, on the left side, we're just going to have a constant. Okay. What's happening is this flow is being driven by a gradient, okay. But that gradient is constant because of the infinite nature of this operation here. So we have a constant. Therefore the right side's a constant as well. Okay, if the left side's a constant, the right side's a constant, and then we just have a trivial integration of these two derivatives, okay, along with the boundary conditions. So constant, therefore this is also a constant. Yeah, so two derivatives of something equal to constant, that's quickly done. So directly underneath here, I should be able to write b sub x is equal to 1 over eta dP dx. Curious about my sign here. I'm pretty sure we're, yeah. So there's my constant. So since I had two derivatives in y, I'm going to have 1/2 y squared plus b times y plus c. Okay. That's the typical thing. And we're going to, when y is equal to 0, we're going to have a 0 there. So c can be stricken from the record. That's 0 there. And then b sub x of h is also equal to 0. So we plug that in there. and we have 1 over eta dp dx times 1/2 h squared plus e times h is equal to 0, which allows us to solve for b. Strike one of these h's, and b is minus this expression right here. So what do we get when we're all done? E sub x y is equal to 1/2. So 1 over 2 eta, write that down. 1 over 2 eta dp dx, and then we'll have h squared minus h times 1 minus h. What's the best way to write that down? Y squared minus yh, or y times y minus h. Y squared minus, let's write it down both ways. We can write y squared minus y times h like that, or we could factor out one of the y's as well. I'll just put that underneath. Y times y minus h. This one makes much more, more explicit what's going on there. Now let's sketch this and make sure everything makes sense. So I'm going to sketch v sub x as a function of y. Here's my 0, here's my h. Okay, vanishes at 0, vanishes at h. And this is a parabolic flow. Why is it negative? Okay. It's negative even though I drew my arrows to the right, because if my gradient of pressure is positive, then the pressure is greater on the right side than it is on the left side, and the flow is being driven to the left. So that's just a question of the direction of the gradient. Okay, so make sure we see that. There's the answer. So it is flowing. If I were to go back to this picture here, and let's make the gradient negative, okay, so it's flowing to the right. If I were to draw some arrows, we would have this profile. So here, gradient of p or dp dx is negative, dp dx less than 0. So what we get is this profile like that, where we've got the 0 here, and then the speed is the greatest in the middle, and it's 0 at the boundaries there. So that's a real channel flow. It's good to talk about the channel first, because when we do the pipe, the math will be a little more complicated. But we also are going to do the pipe. Okay, so we have that. We'll go ahead and send this up. And with this really basic answer, I have another really simple problem for you guys to solve. Namely, leave space in your notes and then do this. You want to calculate the curl of this vector field. So I'll go ahead and leave this picture up. Yeah, leave a little space, but I'll just call this homework. Calculate the curl of V for this channel flow right here, for our channel flow. we could do it right on the spot, but I'll just discuss it right here on the spot. But yeah, you've got your curl of V, and once again, now your Vx, you're just going to have a Vx of y 0, 0. Oh no. Your derivatives, dx, dy, del z. Here you're going to have a Vx of y 0 and 0. Okay, so you can already see you're only going to have that k component of the curl, and it's important, you know, this cannot be a potential flow. It's going to have curl. The only place where the curl vanishes is right there at the center of the flow in the bulk. So this channel flow also epitomizes what's called a boundary layer. Okay? There's curl in this, you know, vorticity in this flow of necessity, and that is where things begin to happen. That's why these flows can generally not stay smooth. Okay, if you push them hard enough, they're going to break up, become turbulent, and all kinds of interesting things happen. So, yeah, channel flow is a good one to start to see all those things. So yeah, calculate the curl. I mean, it's right here, and note that it vanishes. I mean, it doesn't vanish. It's non-zero, especially at the boundaries, and it vanishes only in the middle, which epitomizes just the bulk constant flow, right? Because you see that profile having a local maximum. There's some thin layer here in the middle that you could say is curl-free, but otherwise there's vorticity everywhere. I'm going to consult the clock. Okay, great. So now that we've done this and seen it, we'll talk about the flow through a circular pipe, which is also interesting. Yeah, sorry, calculate the curl. So go ahead, we'll send this up and now do the flow through a circular pipe. And this, of course, is a little more practical because in reality you don't have the flow in infinite planes. So yeah, let's call this flow through a pipe of circular cross section. Circular radius r cross section. And this time we're going to specifically require that the length be much greater than the radius, and we'll actually have an explicit pressure gradient across the ends. Okay. So here we're going to have dp dx, we'll call this the x-axis again, is going to be equal to delta p divided by L. So we're going to have a uniform pressure gradient across this. I think we actually proved that. Let's have a look. So yeah, we'll start with the Navier-Stokes equation again and see what happens. For the record right here, this is what that would turn into. But yeah, let's begin with the Navier-Stokes equation. So we'll have dv dt v dot grad v is going to be equal to 1 over rho gradient p plus eta over rho del squared v, and we'll just start to analyze this thing. see where I've got the best analysis of this. Okay, this is going to be very similar to what we did. In this case, right, it's sufficiently long. So here we're going to start with the Cartesian coordinates, go as far as we can. So here again, we're going to have V sub x is equal to V sub x, this time of y and z. Right, so we can imagine we've got x, y, and z. So we get V sub x of y and z. It's a steady flow, so we're starting with the assumption of a steady flow. And again, these are going to vanish. Let's go ahead and write them out. I'll set this up. Okay, so if we write out Vx dot d over dx, Vx, I'll just write dx plus dy, dz, onto V there. So that's that term. We only have a Vx, but it's not going to change in the x direction, uniformity. Okay, we're not talking about any end effects here. It's a long pipe, so we're assuming that uniformity. We have no Vy and we have no Vz, so this entire thing is equal to 0 again. So the density will actually cancel out of the problem. And same with those gradients again. The gradient with respect to y and z are going to vanish because there's nothing else. The derivatives are going to vanish because there's nothing else in that slot. So this is just a Vx. And we again have dp dx 1 over eta is equal to d squared dx squared plus d squared y squared plus d squared dz squared dx. Of course, since we said Vx of y and z, we're not going to have this. And now we're going to have something interesting. We have something that can only depend on x on the left side and something that depends on y and z on the right side. So both sides are equal to a constant. Okay. So both sides are constant. 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 And at this point, since we have that circular cross-section, we'll turn this into cylindrical coordinates, or plane polar coordinates, if you will. These two coordinates here, okay? So now we'll go to plane polar coordinates, and I'll just pull that out of the hat. So dp dx, we need a minus sign here. I wonder why I have a minus sign. I think I'm taking the pressure greater on the left, less on the right, so it's flowing out the right. Vx of r. Yeah. Okay, so now I'm writing minus delta P over A to L. That's my gradient. Remember the difference in pressure over the ends divided by the length. So that's a constant. And on the right side, I'm just going to transform plane polar coordinates, and I will have 1 over R, d over dr, r, dvx, dr, dvx, dr. Good. Does that need any? Ah, yes. Where vx equals vx of r, just by the symmetry of us having a circular cross section. Because we know that vx is going to vanish on the perimeter on the boundary there, so that's the symmetry that we have. So yeah, now we just have to set this one up and solve it. And see what happens. So since this is a constant here, we can just do this in a couple of steps. We have d over dr, r, dvx dr, minus delta p over a to l times r. That's our first step. And then since that's a derivative there, we have r dvx dr will be this minus delta p a to l r squared over 2, right? And then we can divide by the r, so we have dvx dr is equal to minus delta p a to l r over 2. And so when we integrate that up, we'll get not dvx, we're done with that. dx of r is equal to minus delta p 2 a to l. We'll have another r squared over 2 plus some a times r. Actually, what am I missing there? R dv dr. Ah, I missed something. Let's go ahead and erase this. So here I should have already had plus a constant. Did I have a constant there? Yes. Here I should have had a constant. Good, so if I had a constant here, then when I divided, I actually had a 1 over r. So I should have had a constant here. And then plus a over r. So that one's actually important. Let's do this again. Because now we're going to pick up a logarithm. So bx is equal to minus delta p 2 a to l, got the r squared over 2 plus natural log of r, a natural log of r plus b. Okay. Now let's make sure I've got that. Yeah. A natural log of R plus B. So here's one where we have to go back to our little box around here. So that's the general one. Of course, we know that at the center, when R is equal to 0, we're going to have a finite flow. So A has to vanish because of that. So boundary condition makes A equal to 0. And then the other boundary condition, when R is equal to capital R, Bx vanishes. And that suffices to give us the answer. I'll go ahead and put it in the form that we're going to use it. That'll work. Okay, so now we're going to have Vxr. We already see it right there. We've got the factor of 4. So delta P over 4a to L, and then we've got the r squared minus r squared. So when r is equal to 0, you've got the fastest flow, and when R is capital R, it vanishes on the ends of the pipe, and so you've got that parabolic flow again. This time 0 here and here, and then increasing speeds right there. So we already saw from the channel that we're going to have curl here, vorticity at the boundaries, decreasing towards the middle where we'll have none. You could also get the curl operator for cylindrical coordinates if you wanted to, and you'd find the same thing, but we already found it in the flat channel, which was nice. So this here is the profile, right, the velocity field, and I think we're going to postpone the rest till next time. Let's see how we're doing here. Actually, I think we can wrap this up in the next few minutes. So the last thing we want to do is integrate this and get the flow, the pipe flow. Okay. So this already has a name. Well, say flow. We're going to write it so we have that. Okay, it's the integration of that that gets the name. So what we're going to do is integrate this up, but let's have a quick look at it before we do that. So the flow speed through the channel is dependent on the pressure gradient. It's linearly, and it's inversely dependent on the viscosity and L. So if your viscosity goes to 0, you'd be getting what? An infinite flow rate given a pressure, a delta pressure. Now remember, when we had the flow around the cylinder, the potential flow around the cylinder, we actually had no pressure gradient. Okay. So real flows actually require a pressure gradient. That D'Alembert's paradox was, showing that there was no pressure gradient, and you were getting an ideal flow anyway. So this requires a pressure gradient, and the flow speed is inversely proportional to the length of the pipe and to the viscosity. So that makes good sense. Good. The last thing we'll do is integrate this up. To get the flow rate through a pipe. So what we have here, finally we'll get the flow rate. We'll get the flow rate through the pipe. So what we do is we take Vx of r, that's length per time, and we multiply it by a ring, 2 pi r dr. So that's length per time, that's going to be volume per time. So if we integrate this up, we get the flow rate in volume per time. Let's see where we're going with this. I think that's all we have on our plate right now. I see that, so this is d volume. And d mass, that's where we're headed. We're going to have to go rho times Vx of r, 2 pi r dr. So we're after the mass flow rate. And that'll just be integrated from 0 to capital R. So integral dm. This will be dm dt, really. So mass per time, mass per volume, because there's a time there. I'm just going to write it out. Mass per time. So that should be dimensionally correct, right? That was a volume per time. Oh, I got it. This was volume per time. D volume dt is the unit of time. Okay, so this is mass per time. So let's have at it. What do we have? We've got rho, we've got 2 pi. We have 0 to r. In fact, I'll pull all those things out. We've got the rho and the 2 pi. We've got the delta p over 4 eta L, and now we can have r squared minus r squared r dr, 0 to capital R, 2 pi rho delta p 4 eta L. Let's see if we can just see what's going to happen here. Here we're going to have capital R squared, and then another R squared over 2 from this linear one. And here we're going to have minus R cubed, so minus R to the 4th over 4. And when we get all of this, we're going to have R to the 4th over 4. So what are we going to get? dm dt equals 2 pi rho delta p 4 eta L R to the 4th over 4. So we've got 2 over 16 is 1 over 8. Pi is in there as well. So pi rho delta p over 8 eta L R to the 4th. I'm going to clean that up and put it in a form that we can take home and put in the bank. We'll go right under here. The only thing I really want to change, I want to put eta over rho in the denominator. So we have dm dt, the flow rate in mass flow rate. Pi delta p, okay, yeah. So pi delta p, we want to be able to inspect all of these. 8 there's a reason to do this here. Eta over rho L is part of the formula. Okay. So everything's important here, except for pi. Except for pi over A. This is Clauset's law. Look that up. Make sure I spelled it right. E-U-I-L-E. Yeah. Clauset's law. Okay, so this is an important pipe flow result, r to the fourth. That's what we're going to end with. So yeah, this one you'll find in your undergrad, in your lower division textbook, and they're definitely not going to tell you exactly how it came about. Okay, it took a little bit of doing. So once again, we have the gradient of the pressure, you know, the length. Now we have this r to the fourth dependence, which is pretty strong. So especially if you go down to really tiny capillaries, you notice the flow rate is shut down enormously. Okay, if you go to small capillaries and you make a half of the diameter, half the radius, you got 1/16 the flow rate. So that's a strong, very important dependence there. It plays a role in medicine as well. The reason we went ahead and put this eta over rho in the denominator, this is what's referred to as the kinematic viscosity, and we'll get to that later. We'll return to that. You know, we'll get this expression as well. So I wanted to bring our attention to it here. Of course, it's not natural to have the rho in the numerator, because that's how we set up our integral, you know, for mass. Nonetheless, this eta over rho is itself an important quantity in the Navier-Stokes equation. Good. I think we'll leave it at this, and what we're going to do next time is formulate the Navier-Stokes equation with this quantity there. Good, I think we'll just leave it at that. Let's consult the clock. Okay, yeah, perfect. So we'll see you guys next time. There were a couple rudimentary problems you may want to put in your notes and turn them in. Okey-doke.